Buonasera, benvenuti a GiovedìScienza. Un saluto naturalmente a tutti.
Good evening and welcome to Science on a Thursday, GiovedìScienza. Welcome to all of those who are here and all of those who are following us on the internet, which are, we have been told, many more than are even here. We're here this evening to talk about the discovery that was announced on February the 11th, a week ago to date, which had been mentioned for quite a while now, but the way in which was announced was different, but it was officially announced, in other words, on the 11th. Not an easy discovery to understand. We have to explain the tenets of this theory. This theory needs gravitational words because in previous theories, gravity was a quantity that expanded at an infinite, in an infinite amount, while with the relativity theory, or the theory of relativity, it expands at the speed of light, which is the fastest known speed in nature. And it means that you can see it through electromagnetic waves. We know that general relativity is basically a new theory of relativity that concerns a particular case that incorporates and re-explains Newton's theory. So in the US a few days ago, 14th of September, a mirror slightly modified, in fact two mirrors, we'll see it, slightly modified a laser beam which was 4 kilometers that bounced hundreds of times between one mirror and the other, which means that it was as if the ray were hundreds of times longer, and this is a small vibration, and we will see how small it is. It's something virtually incredible. This very small vibration was the effect of an event that was taking place about 1 billion light years from us. There were two black holes about 30 times the Sun, and the Sun has a mass which is about 330 times that of the Earth. These objects with these sizes met, or should I say more than met, they in fact violently clashed and they merged in a black hole, which is slightly smaller because part of the energy transformed and became these waves that were then perceived. I understand you don't really understand much. I don't really understand much, but we'll try together to understand it with Andrea Chincarini, whom I'm thanking very much for being here. We involved him a few days ago. He works at the INFN, the National Institute of Nuclear Physics in Genoa, but in fact he has been working on gravitational waves for the Europeans processing data. It's especially Italo-French, but it also involves other European countries. It's in Cascina, near Pisa. It is very similar to the American one. In fact, one could say that the American one copied, in inverted commas, the one in Italy. The arms are 3 kilometers instead of 4, and there's only one antenna rather than two, but it's very important because it will have to confirm the American data. So the publication, that explains why the publication was released together with the LIGO and Italy together, the European one. The European corporation, which is VIRGO. It's called VIRGO because we think that it is the sensitivity to pick up goes up to the Virgo galaxy. There are two teams, but we're talking about thousands of scientists who work together. Andrea Chincarini, and this is really the thing which I think requires a specific question, is involved in gravitational waves, but also medical physics. And you shouldn't be surprised because we will see that in analyzing gravitational waves, in the end, you can apply some algorithms that can also be used in the medical field. This is the beginning of an answer to which many of you may have, which is, what's the use of all this? Well, maybe they will also help us with our health. Professor Vincenzo Barone, Enzo Barone, as he'd rather be called. You've probably read what he writes on the Sunday magazine of the Sole 24 Ore, the daily newspaper, the daily financial newspaper in Italy. He has also written many textbooks for the university, but also some books for popularization, because he's always been interested in the history of science and the popularization of science. I have a book of his here, Albert Einstein, Who Built Universes, that you will find outside, which is a book which was published 15 days ago. So if there is a book which is very timely, this is it. So it's an unwittingly timely book, but that's it, yes. You can read it very easily because you know that there are many different Einsteins. There's clearly the scientist, but then there's also Einstein, who's virtually pop, who pulled his tongue out, but then there's a private one who's probably debatable, with a daughter that he was born before the marriage and then abandoned. In there, all the various Einsteins are illustrated here and balanced. The scientist, of course, prevails, but there are also the other aspects that are part of Einstein's scientific biography. Well, I've spoken too much, so allow me now to give the floor to our guests with a question. I would like to ask you to try and summarize this discovery for us. I know that many of us have heard things, and I know that Andrea Chincarini is a physicist who's an experimentalist, but he's also very close to being a theoretical physicist because he works on data, while Barone is certainly a theorist, and he is, in fact, working on cutting-edge topics. Which one of you is going to summarize the discovery? Well, I can do it because I'm outside. I can comment on something I was not involved in, and what I can do for you is I can tell you about what happened in the past, and I think Andrea has to talk about the last 5 months and the last milliseconds before the discovery. As was mentioned before, this was an extraordinary birthday present for general relativity. No one could have imagined it, and general relativity foresees the existence of these waves. They're not exactly like electromagnetic waves. Electromagnetic waves, in fact, which we're quite used to, which we've used to and have used for mobiles. Before that, it was more difficult, but electromagnetic waves are fields that spread in space, while the gravitational waves are space waves, waves of space. This is what is important, which really makes our heads spin. Very difficult to understand, not only for non-scientists, but for scientists too. They're distortions of space, of the space-time, which spread. And these gravitational waves were discovered, were not, in fact, discovered. They were predicted by Einstein in June 1916. That is to say, very soon after the general relativity was formulated in between March and May of 1916. The article was published, the long article, his long article on general relativity, and immediately after, soon after, so he'd been probably working on it, he wrote another article where he studied these solutions. This was the title of the article, that is to say, solutions. Here it is. It's the approximate integration of the field equations of gravitation. So he wrote them, and he had obtained them in November 1915, and then he attempted integration, or approximated, integration. And the solutions which he obtained looked like waves, waves which spread in space and time. They're gravitational waves. He comes back to the issue a few years later, And he writes another article that's called Gravitational Waves. And then he writes the famous formula. These waves are generated by large masses, orbitating masses, for instance, that are accelerated. So there must be some initial distortion, not a spherical symmetry, a large orbitating mass that generates gravitational waves. The Earth does it too in the course of revolution, but it generates gravitational waves for 200 watts. So if we were to gather all the power, probably we'd be able to switch one light on, or a couple. So these waves are quite weak, but they maintain a rather ambivalent and uncertain theoretical definition, so much so that 20 years later Einstein goes back on it and in fact says that they don't exist, and thinks that maybe they were a mathematical artifact. The general relativity theory made it possible for you to change coordinates maintaining the same results. So if you choose particular coordinates, you might obtain a result, but it's not something physical or real. So it was thought that these waves were an artifact of this type. Another major astrophysicist, Arthur Eddington, had written a treaty saying that they were at the speed of thought, because if you switch the systems of coordinates with your mind, they can appear and disappear. So he said that they were phenomena such as these, which travel at the speed of thought. Einstein, for a moment, for a few months, that they didn't exist, wrote an article, sent it to the Physical Review, which was the mother journal on the 11th of February. Here you can see is the one on the left. And he wrote to the Physical Review. They rejected it because they had already doing what they were doing. They did a peer review, and even when there was Einstein's article, it was peer reviewed. Robertson, who was a great cosmologist, said that in fact this result on the inexistence was due to the fact that Einstein hadn't realized that he could change the system of coordinates and make them reappear. Einstein got very angry and never wrote for the Physical Review again. He did realize his mistake, he corrected it, but published in another journal that was much less well known. And what is amusing, to come to what is happening today, is that if you go back to read this article on the Physical Review letters, which is a rather special article with a very clear eye to communication, the abstract is virtually understandable. There was an enormous effort by those who've written it to produce something that could be understood by a wider audience and not just by a limited number of scientists. This article that was published last week gives a number of references, but it gives, which is unusual in nowadays, quotes an article which is 100 years old. This article, which you can see up above, that was published in the Prussian Academy of Science that no longer exists, was followed by another important article, because there's another 100th year anniversary. That is Schwarz's article, where we have the first idea, which will then lead to the notion of black hole. So initially, gravitational waves are a direct consequence of general gravitation. You don't know if they're real or if there isn't, but for sure, they're very, very weak. In those years, it was not possible to imagine sources that were sending gravitational waves that could be picked up on Earth. They couldn't even imagine the instruments that were used to pick them up a few months ago. So it was a purely academic hypothesis. Then in the 60s, 1960s, a physicist who will be mentioned later on, who was called Josef Weber, and who invited these antennae that were enormous metal cylinders, which he thought would help him pick up waves. In fact, they were not too sensitive. They worked for tens of years, pioneers in Italy, for example, Pizzella and Amaldi. But in fact, we had to wait till we had interferometers, in fact, second-generation interferometers, the more advanced ones, which LIGO, for example, switched on in September, 2 days before the discovery of the signal, and which VIRGO then switched on a few months later. Now, this is what happened before. The last seconds plus 5 months is what Chincarini will be talking about. The question I would ask Chincarini is, what are the sources of gravitational waves? We've heard it a bit. We've heard some possible ones. And what are we doing to be able to, in quotes, listen? Because it's not really in quotes, because there is a noise linked to these black holes. Yes, I think that we've been well treated by physicists. So we have been considered better than Einstein's papers, but always after the peer review. I would very rapidly comment what Professor Barone said. The history of this article is peppered by a number of so-called successes or and failures, but they were attempts, that many of which failed and didn't lead to good result. This also gives credit to the perseverance of scientists, because it's not easy to persevere in the road that's so difficult. We know that the signal is very weak. All conditions, surrounding conditions, were discouraging. Even the signal, and we'll see it in more detail, is part of a cosmic event which was extremely powerful, and no one had said that there would be such intense events. So it was really a particular discovery, a very special one. The signal, which you can see in here, yes, here you can see the image and hear it. What you can see here is a signal which was captured by the interferometers, the LIGO one in the state of Washington, and you can hear, translated into sound waves, what you can see on the screen. And you can see two figures there. One, which is a sort of electrocardiogram, which is the signal that the interferometer picked up, and the other one above, which is a time frequency image. This signal, which you hear repeated twice, the first two are low frequency, you can hardly perceive them, just, and then the second 2 times it is repeated at a higher frequency. This real signal is that one. This sort of click, it's a sort of chirp, it's called. It's called the chirp, which, well, we can stop it now, which the idea is that the signal increases in frequency and intensity until it peaks and then falls. Now, this is a very particular signature of the event. It was expected because it came from very dense objects that were coalescing, that were merging, and it's a signal that is used as a test in the instrumental experiments to test the equipment. So amongst the expected signals, this is one of the most important and interesting one. So to interpret all together, I asked them to explain it to me. That background noise, that echo sort of, is simply the noise. It's the interferometer. So the silence is virtually that noise, or that noise is a silence. When there are phenomena which are that violent, there are frequencies that first are low frequencies and then they get higher and higher until you have that click, the chirp, which is when the two black holes merge. Now, this happened. We perceived it from 30 to 150 hertz, but it was present before, but we weren't yet able to pick it up. But this signal existed probably 100,000 years ago, and while it now is reaching the end, it has increased intensity and frequency, and then it entered the sensitivity range of our instruments. So this was an exceptional moment, outstanding, because this signal was so strong that it emerged from the background noise. Most of the signals, and we don't expect most of the signals to have this level of intensity. Most of them are virtually the same as the background noise, and you need techniques to listen to them. These are the techniques. The description of the signal that we saw, there is a phase where these are objects of masses. As I said, there might be black holes, which are much, much bigger than the sun, but these two objects that are very big started spiraling around each other, and then in so doing they might emit gravitational waves. Then they get closer to each other, lose energy, and then as they do, it's a process which leads to an explosion. The closer they get, the more energy, to the point in which you have the catastrophe, which is the merger, and which is represented here by the peak. Here you see that there's an enormous acceleration. Yes, it's half the speed of light. So we're talking about objects which are undescribable in terms of the human experience, of our human experience. Very big masses compared to our sun, 30 times maybe our sun, concentrated in 100, 150 kilometers, which go at a speed which is well beyond the range of our experience. So they're cosmologically cosmological events. So I seem to understand that while gravitational waves had been foreseen, and luckily they were observed, but what had never been seen is the phenomenon that had generated them. So we've discovered and seen black holes close up and seen how they behave when you have two very close to each other. Yes, we had indirect evidence of it, and had for time the famous pulsars that were discovered, which led to the Nobel Prize in 1993. So gravitational waves were part of the standard scientific literature, but they were verified with our parameters, that is to say, in a condition which was very different from ours. So it would have been possible to think of other alternatives in this field, but in the case of the two pulsars, we're in much weaker conditions. They too spiral and lose energy, but the speed isn't as fast and the mass is much, much smaller than what it is. So with referring to what Professor Enzo Barone was saying before, it's a major victory for Einstein, but also for Schwarzschild, because the black holes that he was theorizing at the time, they were only in the imagination of physicists, so while now they're objects, yes. Very lucky, because to produce these gravitational waves, you have to violently shake the space-time, and these black holes are doing this. They're very massive, they're very dense, but at the same time they're rotating, spiraling around each other, and the power of the gravitational wave is inversely proportional to the period of to the sixth power of the rotation. So the faster they rotate, especially in the last instance, where they have a speed which is half of the speed of light, as you can see there, they manage to generate a power which is sufficiently high or great that we can then pick up. And the article refers to both these things, so that is to say, both to Schwarzschild's solution of general relativity and Einstein and gravitational waves. So it's a case which is an extraordinary case. And you were saying, Dr. Chincarini, we were saying about this model. At this point, we're entering what he does, the field of what he does, that is to say, data processing. Yes, you see that the object, there have been many hypotheses were made before we concluded the tests, before we found these black holes, but the other hypotheses were excluded because, in fact, this wave shape, the graph that you can see here, fits certain particular characteristics, so much so that it excludes other possibilities. So, for example, the fact that it was one single black hole or a neutron star. So we have a certain proof that black holes of this size exist and that they behave exactly as relativity had foreseen. And to model these waves, many theoretical and experimental physicists worked for tens of years because it's not at all clear how they merge. So you have to have models and then try the models for a fit. Yes, there are two major difficulties. First of all, is that they are very intense gravitational fields, and then the two objects. So there were two big problems. One, Einstein's were hyper simplified calculations of weak fields. Here we have two very dense objects, a very strong gravitational field, and two objects on top of it. So first, have to solve the problem of the two bodies. Build, so to speak, the formalism which made it possible, the analytical framework to solve this problem, and then simulate and calculate with obstacles of various types, which made it possible to understand what the shapes that correspond to the signal were. More than 250,000 wave shapes were tested. 250,000 models were therefore tested, yes, to optimize this. Clearly, it was done with a wide spectrum, and then once you found the template, that is to say, the wave shape that best fits the data, then you have to go and find the parameters which describe it. I would like to add that this work, although we are still euphoric, this will involve hundreds and has involved hundreds of thousands of researchers, both in Europe, and in the States. There are about 18 countries that are involved. And I would say the work of the colleagues that preceded us is the work that made it possible for us to discover this, because some people spent their entire scientific life trying to improve observational instruments. These are very sophisticated instruments. There's no one single idea that led us to where we are. There are many improvements, many adjustments, many things and many ways in which physics was understood to be able to reach this type of conclusion. So it's not simply interferometers that made it possible to observe this, but it's been an interconnection, an intertwining, cross-contamination between and among various disciplines or subjects of physics, chemistry, all sorts of. So I would like to thank all those who preceded us. Here, this is an artistic representation of to get the order of magnitude of those objects compared to our Earth. I would like to see if you see two objects like this that have a mass which is 30 times that of our sun, and that rotate so much fast, about half the speed of light. Well, to do this, you'd have to reduce the Earth to a ball of about which is 1 centimeter in diameter. Take a pea, and then you've got that level of if the whole of the Earth was reduced to a pea-size object, then you'd get their density. Yes, the problem is that these objects are well beyond our experience, so we can describe them, but we can show them in the representation here. This is the artistic representation. This is a movie which is clearly is not true. I mean, it was imagined, but it shows against the star background. We have the objects are two black holes. You can see them represented here, and you see that they're starting to spiral, the one towards the next, and by so doing, they emit waves, which in this representation gives you an idea of the background, which is very different, because the waves, this is not what actually happens, but it gives you an idea of what might happen. This is where they merge, and when they merge, you see you have a further increase of wave frequency, and the system relaxes, and the two have merged into one black hole. To do this, they burned a mass. The emission of the gravitational waves used up energy, and in a matter of a few milliseconds, they have burnt masses that are equivalent of 3 times our sun. The sum of the two previous, so the new black hole is the sum of the previous two ones minus 3 times our sun, and these waves travel and they reach our interferometers that are here, these two lines that you can see, leading to a distortion of space which can be measured. We've over-exaggerated this because clearly the wave is not as big as we showed you, but it was just to give you an idea. And that is the region of space where, in fact, these objects, here you can see this. This is the Virgo galaxy, 60 million light years. These are more stable objects. The objects are much, much further. Now, I would like to show you another slightly more technical representation of the same phenomenon. But here, down below, you can see the wave shape that we received, the part of the signal. And here you can see the two black holes. Just we've drawn the orbit, but it's not really there. And the colored space below is space, and it shows curvature, and the color itself represents the time distortion. And the objects which spiral faster and faster, now we're slowing them down because here they're near explosion. You can see that there's an extreme distortion of space at the moment in which they merge into one, and we have these ripples, these additional waves that are due to the stabilization of the event, but the ripples come up to, well, can be detected right up to us. This is a slightly more technical version of what I showed you before. And you see in the band below is what is actually picked up. This is a simulation because nobody's ever seen these objects. We don't even know But it gives us an idea. At least we can imagine what is happening. And we are confident that this is a reasonably good representation because the signal matches the one which was predicted by general relativity, which is the theory on the basis of which we produced the simulation. So we know that it's an artistic representation, but the signal that was so well described by the theory, it indicates that it can't have really been very different from what we're showing you here, although we don't know. This is another big result because we weren't expecting such a good fit between the experimental data and the theory. There was a bit of disbelief at the beginning about how close the fit was. Are the experimentalists more surprised than the theorist, or vice versa? Which one of you is more surprised? I must say that the surprising thing is this absolute fit with the signal. If we hadn't had the 5 months analysis and 50 million hours of CPUs, to be sure, it would seem to be appreciated, because 2 days after the machine was switched on, we picked it up as if you had a wanted person, and as you go out you leave the police headquarters, you find the wanted person there and then. So, but it's a further test, because there are a series of other things that are different from what we've done, which to a degree turn it round. It's a discovery, but it's also a test which has validated the models, which are maybe. It's not right to say that they're models, because it's based on a general theory, a fundamental theory, which it's one way in which we have tested the theory in a situation where there are very intense fields of general relativity. So general relativity has always been verified, especially in weak fields, and we have instruments that are so sensitive that they can pick up very small changes, such as atomic clocks, the latest generation ones, while this was in drastically intense fields and on objects which are very, very distant from us. I don't know if it was mentioned, but 1.3 billion light years. So they tested the theory on very large scales. Professor Chincarini, could you now please tell us which sources we could discover through this new astronomy? Can we call it gravitational astronomy? Well, yes, we have optical astronomy, where optical is used in the more general sense, because it's not only visible light, but also the electromagnetic ones, infrared, radio waves, X-rays, gamma rays. Now we have a new band, which is different, as Professor Barone was recording, a gravitational field. So what type of objects might we observe, and with what instruments?
Sono, diciamo, diversi, ovviamente. Ci sono diversi oggetti che si presume esistano, anche se io...
There are several objects that we presume exist, although I would like to say that we can now look in wonderment at the cosmos. We're expecting to see some objects, but there might be many others. So really it's a new season. Here, amongst the most common wavelengths, we have seen the so-called coalescing compact binaries, which are bottom left ones. This is the wave shape that we had before. This is a long period of stable orbit until there's decay, and then we have the final catastrophe with the merger. And this is the standard one. The idea but then also we have other sources, for example, continuous wave sources, pulsars, for instance, neutron stars, very compact ones that rotate very quickly on their axis. 1,000 rotations on their axis a second. Yes, very compact objects. Yes, 10, 20 kilometers. They're very compact. Maybe they reach a couple of solar masses, but compressed. Extreme objects for us. And if you have a lack of uniformity, so you have a density of mass that is not distributed uniformly in the star, this can generate waves. They're very weak, because if they were as a big mismatch or misfit, they would explode. But this small amount give us a radio signal. So we have a very specific lock on the phase and frequency, which enables us to carry out a very specific data analysis. Weak but more easily detectable waves then. Yes, because in this case, the frequency would be twice that of electromagnetic waves, so we have a lock, which is very specific, which means that in time we can gather data over time and increase the reaction between noise and background, and also measure weaker events. Also because the event that we listen to is an unexpected event which can happen and then you're lucky, and while in this case we would know exactly what we should be listening to, and instead of having an event which lasts fractions of a second, we could follow it for months. Yes, the previous generation of interferometers already made it possible for us to follow this, and we set an upper boundary for the spheres, the size of the spheres that we would observe. You can put upper boundaries. With these, we have information which is quite useful. Another source which we're expecting, the so-called burst sources due to explosions. In this case, the signal is, given what they are, is much stronger. They might be supernovas or major catastrophes that, if happened symmetrically, could emit gravitational waves and give us a wave shape which is similar to the one that we have on the top right. And lastly, which more difficult to identify, but would be very important in terms of cosmology, is the stochastic backgrounds. That is to say, the background noise, which is very similar to the one that we see with the microwave, say. And the echo of the Big Bang, from an electromagnetic point of view, gives waves that have been studied for many years, studied in great detail from very many satellites. And we think, the field is still open, but we think that the analogous one behavior can be also the background of gravitational waves that would be a background noise. And so here, Professor Barone, does that mean we will be closer to the Big Bang by observing the background rather than the microwave? Yes. The practical problem of all this, but maybe my colleague will be talking about it, is that all these signals are on a very wide range of frequencies that goes well beyond the frequencies that currently we can measure with interferometers. Current interferometers have signals that go from a few tens of hertz to about 150 hertz, and to have a complete gravitational astronomy, you would need to extend to have very low, few hertz signals or fractions of hertz. So It may happen, but in the future, yes, I'm sure that it'll happen, and there are already projects and plans in this respect. But what I want to add is that as far as neutron stars, we will also have important information on them, because other than black holes, we don't really understand neutron stars. Are they ordinary matter, or are they, for example, quarks? From this point of view, this type of gravitational astronomy will lead to the development of information of objects that are less exotic, in quotes, but we still don't fully understand in terms of their structure. Now, this level of sensitivity that the Americans, but also VIRGO, is reaching, I think, because I think Europe will soon be working on this. How do you reach this level of sensitivity? You gave us an idea with these arms, 3 kilometer long, and this laser beam bouncing back several times. Can I just show you here the big cylinder? Let's start with it. This is a bit of archaeology. These were the first instruments to pick up gravitational waves in the 60s. We've been hunting for gravitational waves for years. The pioneer was, well, Weber was the pioneer, or Weber. He had an aluminium cylinder hanging and then had piezoelectric sensors. So it was certainly a DIY product. We might make a smile today, but it was an extraordinary intuition and a breakthrough, because it gave a number of research projects an outlet. The principle is the principle of a diapason, a mass that was studied to resonate at the frequency that you wish to observe. When the gravitational wave is perpendicular, then it means that it's stretched and that it resonates at that given frequency. Further developments on the basis of this idea included a transducer being added to measure this, not only directly, but through a much smaller mass that amplified the movement. So a small movement was then translated into a big movement with a smaller mass. These led to a number of studies that were extremely sophisticated studies, superconductors, squibs, all the rest of it, all the topics of physics that, well, Amaldi was the top one, but the whole Rome group, Pizzella, for example, Coccia, and this is the group here. And in this group, there's also Fulvio Ricci, who's in charge of VIRGO, so he's got the whole history. Ricci is the spokesperson of the experiment and represents the community of physicists who are working on it. And all these years, we developed this idea, and 3 gravitational antennae were made, Explorer, Auriga, and Nautilus, one in CERN and one in Frascati in the labs, the INFN labs, and the other one in Padua. The noise, yes, and even cooling it, they haven't got the type of sensitivity of the new ones. Well, numerically, they have reached, if you put them together, they have sensitivity which altogether is like an interferometer for first generation. But only at a very specific frequency, that is to say, the antennae are resonating objects, and they became even more resonating to be sensitive, but this drastically refused the band, that is to say, the frequency. And what they're around 935, 950 frequency, very high frequency that we would now frequencies that we would nowadays consider unsuitable. But it was the first attempt, and not only did it make it possible to develop very sophisticated technologies, but the first network of objects work together, and they gave us the first result. Yes, this is important to say. It's not enough to have one in one place, but you need another one, another antenna of the same type or with the same level of sensitivity at a distance in space, should be able to perceive this distortion of space and time at a certain time in syntony or synchrony, I should say, with the other one. And this is a major problem which was present both in the antenna but also in the interferometers. That is to say, we have no possibility of screening gravity, which means that our objects are always immersed in gravity and of all the noises that they hear. So since we can't screen the signal, we have to use coincidences to say, because if there is, for example, a noise in Louisiana, it won't be in Cashina, so you can discriminate between noise or pseudo phenomena. And yes, a single interferometer, I mean, if it's an extreme signal, we can work with it, but it couldn't really say much in principle unless it is validated by other interferometers that are distributed appropriately around the Earth and which can validate the signal. So once again, it's a question to you both. So far, we have a certainty of one signal. There's no certainty in science, but we say that there is a level of certainty and that the signal is what it is, but it's one event. So question both to the experimentalist and to the theorist. In this case, we have the importance of the European work, because we'll have to gather more signals, and above all, we will have to see them in the US and in Europe with the right time lag between one area and the other. This will also help us identify direction. Let's hear Barone. Well, first of all, this signal will not be isolated. He's part of the group, so he can't speak. Yes, he can. No, he can't. But seeing it from the outside, we presume that there will be other signals. So clearly, it will be essential to VIRGO starting off. Now he will show us how, because we spoke about archaeology, but now he'll be talking about interferometers. And if there is a network, a global network of antennae, now there is a network of interferometers to increase sensitivity, but also to have triangulations and coincidences, because two interferometers, like the American ones, only give the direction. When we will have a certain number of interferometers, then it will be possible to localize more specifically where it comes from, and they will have to be comparable instruments with the same potential, which is the one which he will be now talking about, which I believe are extraordinary.
Seguo quanto avevo detto, ma possiamo vedere adesso il modello di funzionamento
is an artistic representation, so don't take it as if it were reality. But you see there is a beam which goes through a semi-reflecting mirror. It splits it in two. It goes right up to the end, to the optical cavity where it's reflected, and it recombines in the mirror, and then the result is passed to a photodiode, which is a sensor, and which gives us the intensity of the light. If the light is monochromatic, by varying the optical path from one mirror to the other, you have a variation of luminous intensity at the output on the photodiode. This is the principle of the interferometer. That is to say, if we have two cavities that are perfectly aligned and the beams annul each other, so we have the dark edge while the cavities move, and in particular if they move in the opposite way, what we expect gravitational waves, which favor us because they tend to squash one side and to extend the other one, so they have a double effect on the optical path of the two beams. When this happens, they are no longer in phase, and therefore we have a light which sums itself rather than cancelling itself. This is a very simple principle, but this is not how an interferometer is made. It's much more sophisticated because this configuration would not be able to reach the levels of sensitivity which are required. In particular, it's formed by another two mirrors that form optical cavities where the light bounces many times, and it's accumulated within this cavity. This makes it possible to measure the center mass of the mirror. Can be measured very carefully. They're hanging mirrors, very sophisticated system. They must be free from noise, and we can see them described in the picture on the right, or in the graph on the right. The idea is that the final beam will have both information on the differential optical path, but also information on any disturbance which takes place. This means that there was a painstakingly detailed work with a large an enormous number of young researchers who patiently worked to improve the measurement of the impact of any outside event on the laser, so as to be able to identify the signal. Yes, what we need is extremely sensitive objects that can distinguish the external effect from the gravitational wave. It's not quantitative, but it's as if you were trying to listen to a confetti falling on the ground in a disco setting. Yes, so the advanced interferometers, the new generation ones, LIGO being one of them, and VIRGO is also being upgraded. On these interferometers, the second generation ones, we made an enormous effort to deal with all the noise problems that we had with the first generation ones. They work very well, but they were limited by a certain amount of noise, thermal noise, or light, shot noise, stray light, photons. We can see it. In fact, Professor Barone was saying we have a movie on the film clip on this. No, it just shows you the variation of the distance. Here, it doesn't tell us the level of sensitivity that we need. Here you can see the hydrogen atom. Let's have it over again. And his electron. Again, it's graphics, and it's not what actually see. Here you see the proton. If we magnify it many times, we get to this, 4 to the minus 18 meters, which is the size at which the center mass of the mirror moved, which is a millionth, it's a billionth of a billionth. A billionth of a billionth of a meter. So it's something which people talk about, but once again, it's well outside what we can experience directly. So to be able to appreciate this very small difference, we have had to fight against all a number of different noises, as we call them, problems, new problems, because many have been discovered as little at a time to be able to discriminate between them, but it's not enough, because here you can see a air view of VIRGO. We're big, even if seen from above. Our VIRGO in Europe has 3-kilometer arms, the American LIGO 4 kilometers, but otherwise they're very similar. Very similar level of technology, although different solutions have been found to different problems. And they have been thought to work in a symmetrical manner. But to reach these results and this level of sensitivity, the inside is extremely complicated. Here I've brought you a few photos. This is a diagram of what is in the central building, the one that you can see there in the photo. Here the laser is so-called purified. So there's only one pure component of the laser frequency is used. It's projected. Here you have the splitter at the center, and that sends the beam into the two arms. And on the other side we have the section that receives the light and recombines it. All these objects are not only inside vacuum containers, because air interacts with light and causes scattering. So we can't have any scattering, we can't lose photons on the way. So we need a vacuum. And again, sophisticated techniques. Is it a vacuum that corresponds what we have on the moon or more? Oh yes. In fact, 10 to the minus 7 torrs, and there will be more in the future, for 3 kilometers. So it's a large volume, because the tube has 1 meter, is 1 meter in diameter, because the CERN tube is longer but much smaller. Yes, vacuum on these sizes is not easy. All these objects have to be suspended in an appropriate manner so that they are not affected by any variations outside the experiment. Again, very sophisticated. We have to thank to those who invented it. They sort of have mechanical filters, magnetic and mechanical filters that act as buffers and that progressively filter. Here you can see there is an inverted pendulum, and then there are a number of filters with very special materials which are used to insulate as far as possible the mirror that is hanging from these filters and to shield it from outside vibrations. There's an actor part, there are sensors, and there's a more passive one. Now, here you can see the old mirror, but it gives you an idea of what it means working inside these tubes. At that point we have air, because couldn't work otherwise. But the mirrors are hanging from very thin wires. This is the last filter, and these objects have a new configuration. In the new configuration are made of glass. 200 micrometers, like a hair, that are able to hold up about 50 kilos each. Very sophisticated objects that hold the mirror up, and they then are linked up to a structure that holds it. The mirrors are extremely sophisticated and have a technology that no one laboratory in the world can manufacture. But we've got an idea, and again the question which we might develop. All these technologies, have they any fallout? Is there any industrial or practical result? Oh yes. In fact, the technological transfer is one of the main advantages that we have for our society. INFN invests a non-negligible amount of money in this. It's not only VIRGO, and doesn't only happen with VIRGO, is that in fact all major experiments have a fallout because it enables industries that manufacture what we need to grow and to develop knowledge, and also to use this knowledge for other reasons, or for other products. The magnets, for example, in Cascina, or the mirrors, or the ideas of the hanging systems. So a great investment in fundamental science that has a fallout, maybe sometimes a long time after, yes. Well, both in Europe and around the experiment, they develop, and here you can see the mirror. You have a photo of the super attenuator. This is the structure that contains all these filters, and this makes it possible to insulate the objects. I've said this is not the only one. There are active and passive structures. This is a passive one, and it has made VIRGO already in the first generation to be more sensitive and pick up more of the lower frequencies than LIGO. LIGO, on the other hand, has other things, and it picks up other frequencies better. But here you see what we describe as the sensitivity curve. What is the minimum variation which the instrument is able to pick up in measurable space? Here you have the frequency, the variation of space, expressed as a variation on a meter. So when you see that it moves 18 meters on 18 kilometers, you can transfer it to see what and then where, what type of signal it is. Here you see there is a very obvious peak. Yes, the lowest peak is here, around about a few hundred hertz. The gravitational signals that we saw at the beginning started with 30 and reached 150. So it went through, it swept through the maximum sensitivity area. Then there are spaces where there are resonance, there's resonance that's picked up, and then some frequencies must be excluded, where there are the blue peaks, yes. These are resonances of the system. It's like the fibers that hold up the mirrors, so they can vibrate, and they overwhelm the other signal. This is a living machine. Unlike other more inert instruments, this instrument lives. It's alive because it has thousands of physical phenomena that would could hide the signal, and so they have to be monitored, eliminated to see the signal. So it's really a non-passive instrument, but something that interacts with the signal and must be monitored continuously. Yes, it's really very different from what happens at CERN. In fact, totally different. We produce the event, so we have to wait for it. Here we have a machine that has its own life and perceives background noises too. Those were the ones we have to fight, and then when you have an unexpected signal, you must be ready to pick it up and recognize it. Yes, because it also has a quantum life, because these spatial variations that must be measured are in subatomic measurements, so a fraction of the size of a proton. So you must also take into consideration all the quantum interferences. We're talking about photons, not of light beams, yes. We've virtually finished now. I just have one more question. What will we have after LIGO and after VIRGO? What awaits us? There are several hypotheses that are currently being studied. We have, well, certainly, there's a spatial experiment that's underway. Maybe if I can show this slide here. The Earth interferometers are limited in terms of the frequencies that they can observe. Other phenomena, because we can't always shield them, are also picked up. So the idea is to do it in space. It's a challenge. We're talking about objects that have to not only be put into orbit, but far away from the Earth. Yes, Lagrange would help us here because he was one of the founders. We're going to mention him because he was one of the founders of the Academy of Science in Turin. Yes, much lower frequencies will be picked up, and as I said, we expect different signals, and then there are other attempts. One of the most interesting, because it has only recently been launched, is this of a finder to prove that it is possible to have interferometers in space. And this satellite was launched and recently has issued results, and you see the masses float because it's out of gravity. There's no gravity. We're trying it out. We're trying to see whether it is possible to verify the technology. This project has been modified several times. I don't know whether it'll be finished or not. It's very ambitious. It's at 1 million kilometers, one part of it from the other. We're talking about 2034. Yes, but they're rough estimates. Another thing which is already being used and has been used for several years, maybe more sophisticated system, more specific, which the cosmos also uses as a source of data. That's to say, using the pulsars that rotate very quickly and see the lag time from Earth. And in this case, these very large wavelengths, we can measure the time of the wave takes to get to the Earth, and on that basis work out if it's curved or not. But this is already underway, but we don't know what the results are. We can stop here. At least I think we've got a general idea. We didn't understand everything, but I think we have the intuition of the fact of what is happening, of what will be happening. And so now I would like to thank very much Andrea Chincarini and Enzo Barone.
Enzo Barone, grazie ancora.